Okay, so the first one you won't have to worry about on the quiz, but just in case we're talking about it related to weights, when we pour the water into each shape. So for A, as we pour the water in, it's going to quickly fill up as it begins, and then it's going to slow down, and then it's going to fill up quicker again. So you can see it's getting quick, slowing quickly. Sorry, this is the difference. This is starting quickly, then slowing down, then quick, then slow down. This one is going quickly, slowing down, and then quick again. So it should start out with A being choice 4 here. All right, with this graph. B, as you start filling it, it's going to fill up at a constant rate because it's a prism here. So it's going to fill up just at a nice constant rate. So that's going to be choice 5. All right. For I, it's going to be slowly increasing. And then it's getting quicker and quicker and quicker, though, because you can see actually the opposite. If you do the tangent lines, notice the tangent lines are getting quicker. They're getting steeper and steeper and steeper. So it's filling up quicker and quicker and quicker, and then eventually it kicks up at a constant rate. So this is going to be this choice right here for C. Notice it takes a little while to fill up at first, but then the height's going to pick up quicker since it's slanting inward. So that should be choice number 1. For letter D here is this shape. Here it's going to start quick, then slow down to quick, and then it's going to do the same thing again a little bit quicker this time. So quickly, slow down, and quick again. So that's going to be here, quickly, kind of slowing down, then pick up pace, slow down, and then pick up pace again. So that's going to be choice D. And then letter E is going to be, get out of there. For this one, it's going to fill up quickly at first, and then it's going to slow down because we're expanding this, and the height's going to go slower and slower until eventually it goes at the constant rate. So that's this one where it's going, you could draw your tangent lines, the slopes are getting lower and lower and lower, they're flattening out, and then it's a constant rate. So that should be this one on the end. So 4, 5, 1, 2, 3. Question number 2. Spherical hot air balloon is being inflated. The air blown to the room at a rate. Air is blown into the balloon at a rate of 2 cubic feet per second. So this is a volume and it's a rate. So we're being given dV dt is equal to 2. We want to find, for this one, how fast the radius is changing. So that's dr dt. And we know at this point that the r, when r is equal to 3, and the equation we're using, because we're talking about a balloon, which is a sphere, is that the volume, this should actually be a colon, equals 4/3 pi r cubed. So all we're going to do is take the derivative of our equation. So dv dt is equal to the 4/3 pi is a constant, so that stays in front. And the derivative of r cubed is 3r squared. And then our chain rule, because it's not t, needs to be dr dt. Okay, now, can we plug in r? Yes, we know it's 3. Can we plug in dr dt? Well, that's what we're trying to find, right? And we know that dv dt is 2, so we have everything we need to solve for dr dt. We have r, we have dv dt, so we're just going to plug in. So 2 equals 4/3 pi times 3. And here you can see that we're dividing by 3 and multiplying by 3, so these are going to kind of cancel each other out. R is 3, so 3 squared. And then times what we're trying to find, which is dr dt. So we have 4 times 3 squared, which is 9. So we get 2 is equal to 4 times 9 is 36 pi, and then times dr dt. We're just going to divide both sides by that 36 pi. And we're going to get 1/18 pi. And because we're units, and this is a radius, our cubic units, feet cubed per second, this is a volume, so our radius is just going to be in feet per second. And that's dr dt. And then we want to make our statement for ourselves. So the radius is changing, and we're not just changing, but increasing at a rate of 1/18 pi, make sure the pi is on the bottom, and then feet per second. All right, for part B, how fast is the surface area changing at the same time? So the given's going to stay the same. We have everything we already given. Notice that we are also knowing that we just found the dr dt here. So the surface area formula is going to be 4 pi r squared. So if I take the derivative of this formula, we'll call this ds, or actually since it's area, we'll call it dA dt, is equal to 4 pi, and the derivative of r squared is 2r dr dt. Now, we're trying to find, right? We're trying to find dA dt. We know what r is. It's the same as it was before. It's 3. And we also know that dr dt was what we just found, which is 1 over 18 pi. So we can solve for dA dt by plugging in the 4 pi 2 times r, which is 3, times our 1 over 18 pi for the dr dt. Okay, we can simplify all this stuff because there's a pi that we're dividing by and a pi that we're multiplying by. These are going to kind of cancel each other out. So we're going to get dA over dt. 4 times 2 is 8, times 3 is 24 over 18. And if you reduce this, you can take a 6 out of both. So we get dA over dt is equal to 4 and then 3, 4/3. And remember, this is an area, so it's in feet per second in terms of units, and the volume is feet cubed per second. This would be feet squared per second. And then we would say the same thing we did before, that the area is increasing at a rate of 4/3 feet squared per second. All right, that's the first page.